Hello everyone and welcome to our module on predictive values. If you think about diagnostic tests which are used to identify patients with and without disease, what doctors and patients really want to know is, if I have a positive result, what's the likelihood that I have this disease? And if I have a negative result, what's the likelihood that I don't have this disease? In another video, I talk about sensitivity and specificity, which are important characteristics of diagnostic tests, but they actually don't answer these two questions shown on the slide. In order to answer those questions, we need to look to something else, and that's the positive and negative predictive values associated with a diagnostic test. In the video on sensitivity and specificity, I talk about how to set up a 2x2 table like what I've shown in the slide here. The disease is along the top with patients who have disease in this column and patients who do not have disease in this column. The diagnostic test is along the side of the table. Patients who test positive are in the top row, and patients who test negative are in the bottom row. And when you set up a 2x2 table like this, the true positives are in this quadrant, the false positives are here, the true negatives are down here, and the false negatives are down here. So once you set up a 2x2 table like this, it's easy to calculate the positive predictive value. It's equal to the number of true positives divided by the true positives plus the false positives. And so basically what this number means is, of all the patients who test positive by our diagnostic test, what percentage of those patients are true positives? A test with a very high positive predictive value is a test where most of the patients who are positive by the test are true positives who actually have disease. In contrast, the negative predictive value is equal to the number of true negatives divided by true negatives plus false negatives. And so what this number is telling you is, of all the patients who test negative by our diagnostic test, what percentage of those patients are true negatives? A test with a very high negative predictive value is a test where most of the negative test results are true negatives and very few are false negatives. So let's apply these principles by going through a sample question. A test has a sensitivity of 80% and a specificity of 50%. The test is used in a population where disease prevalence is 40%. What is the positive predictive value for this test in this population? Well, the easiest way to answer questions like this is to create a hypothetical group of 100 patients. They tell you that disease prevalence is 40%, so 40 of those patients will go here. That will be the total number of patients in this column that have disease. The remaining 60 patients will go here. That's the total number of patients in this column. They then tell you that the sensitivity is 80%. And so as I explained in the video on sensitivity and specificity, that means 80% of these 40 patients will be true positives. That number is 32. The remaining 20% of the patients, which is 8 patients, will be false negatives, and so they go in this quadrant here. They also tell us that specificity is 50%. That means of the 60 negative disease patients, half of them, or 30, will be true negatives, and the remaining half will be false negatives, so 30 goes here. So now we've filled out our 2x2 table using the information given to us, and it's very straightforward to calculate the positive predictive value. As I told you on the last slide, it's equal to true positives divided by true positives plus false positives. The true positives are 32, so that number goes here. The false positives are 30, that's this number right here, so 30 plus 32 is 62, so that goes on the bottom. And so we now have a positive predictive value of 32 over 62, or 52%. A very important point to understand is that predictive values are dependent on the prevalence of disease in the population where you're using the diagnostic test. This is different from sensitivity and specificity. They are independent of prevalence of disease, but that is not true for positive and negative predictive values. To make this more clear, let's imagine we have a test called test X with a sensitivity of 80% and a specificity of 50%. And let's imagine that we're going to use it in two different populations. In group 1, the prevalence of disease is 80%, but in group 2, the prevalence is only 20%. Well, what I'm going to do is the same thing that I did on the sample question 2 slides ago. I'm going to create a hypothetical group of 100 patients. And in group 1, the prevalence is 80%, so 80 patients are going to be disease positive, and 20 will be disease negative. Because the sensitivity is 80% of these 80 patients will be true positives and go in this quadrant here. The remaining 20%, which is 16 patients, will go here. And then because the specificity is 50%, half of this group of 20 will be true negatives, that's 10 patients. The remaining half, which is another 10, will be here. These patients are negative for disease, but they test positive, so they are false positives. So now that we have the table filled out, we can calculate the positive predictive value. It's 64 over 74, or 86%. If I do the same experiment in group 2 where the prevalence is 20%, over here we have only 20 patients who are positive for disease. The other 80 are disease negative. I'm then going to split up the patients the same way I did for group 1. That will give me 16 in this quadrant, 4 here, and 40 and 40 in these two quadrants. This yields a positive predictive value of 16 over 56, or 29%. And so as you can see from going through this example, the positive predictive value fell from 86% to 29% when we shifted from a population group with a high prevalence to a population group with a low prevalence. In both of these groups, the sensitivity and specificity are unchanged. They're 80% and 50% for both groups. But the positive predictive value changed a lot. It was much higher in the group that has a high prevalence of disease. On this slide, I've gone through the same sort of thought experiment around test X, but in this case, I've calculated the negative predictive value in both populations. In group 1, where the prevalence is very high, the negative predictive value is only 38%. But in group 2, where the prevalence is much lower at 20%, the negative predictive value is much higher at 91%. So whereas positive predictive value was highest in this group where the prevalence is high, negative predictive value is higher when the prevalence is low, which is in group 2 in this example. So this brings me to another key point, which is that positive predictive value is higher when disease prevalence is higher, and negative predictive value is high when prevalence is lower. You can memorize this if you wish, but it makes sense if you just think about it. When prevalence is very high, there are lots of true positives in the population, so naturally the positive predictive value is going to be higher, because the more true positives you have, the higher the positive predictive value. When prevalence is low, there are lots of true negatives in the population, and therefore negative predictive value is going to be high, because this number depends on the number of true negatives in the population. And then also in the video on sensitivity and specificity, I talk about choosing a cutoff point for a diagnostic test like blood glucose level that we're using to distinguish between diabetic patients, shown by the red curve here, and normal individuals, shown by the blue curve here. So if we pick a cutoff point like right here, we say that anyone who has a blood glucose level above that cutoff point, we're going to call a patient with diabetes, and anyone below that point, we're going to call a patient who does not have diabetes. When we do this, we're going to get a number of true positives. That's all these individuals under the red curve here of patients who have diabetes. But we're also going to get some false positives. That's these patients right here under the blue curve that are above the cutoff point here. So this cutoff point will give us some number for positive predictive value equal to the true positives, and there are a lot of those as indicated by the red curve, divided by the true positives plus the small number of false positives. And what you need to know for your board exams is that if you move the cutoff point in this direction, it's going to lower the positive predictive value. So to make this more clear, let's hypothetically consider that we're going to move the cutoff point from point A here, indicated by this line, to point B here, indicated by this line. Well, using cutoff A, we have a very small number of false positives, and we have a fairly large number of true positives. So let's just make up some numbers here and say that the true positives are 10 and the false positives are 5. That would give us a positive predictive value of 10 over 15, or 66%. When we move to cutoff point B, the number of true positives gets higher because now all these patients are going to be true positives according to our test. But the number of false positives also goes up because there are more normal patients now who are on this side of the cutoff point, and therefore they are going to have a positive test result even though they're actually normal subjects. So at cutoff point B, we might have a true positive number of 15. This has gone up from 10, but also a false positive number that has increased to 10 from the number 5. And this will give us a positive predictive value of 15 over 25, or 60%. And so I went through this thought experiment here with you just to show you that when you move the line in this direction, in other words, when you make the cutoff lower so that a positive result captures more true positives but also more false positives, that is going to lower the positive predictive value. In terms of negative predictive value, however, when you move the cutoff point in this direction, that increases the negative predictive value. And the reason this is the case is because as you move the cutoff line in this direction, More and more of your negative patients are going to be true negatives. There will be a smaller number of them overall, but a higher percentage of your negative test result patients are going to be true negatives, and that's going to increase your negative predictive value. So let's go through a sample question that emphasizes these points. So suppose the American Diabetes Association proposed lowering the cutoff value for fasting glucose level that indicates diabetes. How will this change affect sensitivity, specificity, positive predictive value, and negative predictive value for the diagnosis of diabetes? So what they're describing is what we just talked about in the last few slides. They're describing moving the cutoff point for the diagnostic test of fasting glucose level further to the left, and they're asking what impact this will have on the characteristics of the diagnostic test. So in the videos on sensitivity and specificity, I talk about how moving the cutoff point to the left increases sensitivity and decreases specificity. And then, as we've just been discussing on the last few slides, when you move the cutoff point in this direction, the positive predictive value decreases and the negative predictive value increases. Make sure you understand the reason why this is the answer to this question. These type of things are often shown to you on your board exams, and if you just know how the test characteristics change with a shifting in the cutoff value, you'll be able to answer the question easily. And I'll finish with this one slide talking about how predictive values vary with sensitivity and specificity. So we've already talked about how predictive values vary with disease prevalence, but they also vary based on the sensitivity and specificity of the test. So factors that increase or maximize the positive predictive value are shown here. Diagnostic tests with a high sensitivity and high specificity will give you an increased positive predictive value, and that's because these tests identify more true positives and less false positives. And shown over here is the equation for positive predictive value. It varies with the true positives and false positives. And then, as we've already discussed, when there's a high disease prevalence, this tends to give you a higher positive predictive value because there are more true positives in the population that you're testing. If you want to maximize or increase the negative predictive value, you also want to use tests with a high sensitivity and high specificity. That's because these tests will give you fewer false negatives and more true negatives, and the negative predictive value varies with the true negative and false negative rate. And then, as we've already discussed, when the disease prevalence is low, that tends to lead to an increased negative predictive value because there are fewer false negatives in the population you are testing. And that concludes our module on predictive values.